Our goal is to simplify this expression for the squared error between those endpoints. Just to remind ourselves what we're doing. We have these endpoints, and we're taking the sum of the squared error between each of those endpoints and our actual line y equals mx plus b. And we get this expression over here, which we've been simplifying over the last couple of videos. We're going to try to simplify the expression as much as possible, and then we're going to try to optimize. We're going to try to minimize this expression, or find the m and b values that minimize it, or that's, I guess you can call it, the best fitting line. Now to do that, it looks like we were just making the algebra even hairier and hairier, but this next step is going to simplify things a good bit. So just to show you that, what is if I want to take the mean of all of the squared values of the y's? So that would be this. That would be y1 squared plus y2 squared, plus all the way to yn squared. So I've summed n values, n squared values, and then I want to divide it by n, since there are n values here. And this is the mean of the y's squared. That's how we can denote it, just like that. That is the mean of the y squared. Or if you multiply both sides of this equation by n, you get y1 squared plus y2 squared plus all the way to yn squared. Yn squared is equal to n. Let me do this in different colors. So this is equal to n. This n times the mean of the squared values of y. And notice, this is exactly what we have over here. That is n times the mean of the squared values of y, or the mean of the y squareds. It's exactly what that is. And we can do that with each of these terms. What is x1 y1 plus x2 y2 plus all the way to xn yn? Well, if we take this whole sum and we divide it by n terms, this is going to be the mean value for x times y. For each of those points, you multiply x times y, and you find the mean of all of those products. That's exactly what this is. Well, once again, you multiply both sides of this equation by n, and you get x1 y1 plus x2 y2 plus all the way to xn yn is equal to n times the mean of xy's, the mean of the xy's. So n times the mean of the xy's. And I think you see where this is going. This term right here, is going to be equal to n times the mean of the products of xy. This term right here is n times the mean of the y values. That's what this term right here is. And then this term right here is n times the mean of the x's squared. The mean of the x squared values, I should say it. This term right here is the mean of the x's times n. Right? If you divided this by n, you'd get the mean. Since we're not dividing it by n, this is the mean times n. And then this is obviously, we don't have to simplify anything. So let's rewrite everything using our new notation, knowing that these are the means of these, of y squared, of xy, and all of that. So our squared error of the line, our squared error to the line, from the sum of the squared error to the line from the endpoints, is going to equal to, this term right here is n. Let me color code it a little bit. This term right here is n times the mean of the y squared values. This term right here is, I'll do it all in this green color, is equal to negative 2m, that's just that right there, times n times the mean of the xy values, the arithmetic mean. And then we have this term over here. And I think you can appreciate this is simplifying the algebraic expression a good bit. This term right over here is going to be minus 2b minus 2bn minus 2bn times the mean of the y values. And then we have plus, we have this term right here, plus m squared times n times the mean of the x squared values, and then we have, almost there, home stretch, we have this over here, which is plus 2mb times n times the mean of the x values. And then finally, we have plus nb squared. Plus nb squared. So really, in the last 2-3 videos, all we've done is we've simplified the expression, for the sum of the squared differences from those endpoints to this line y equals mx plus b, right over here. So that is kind of, we're finished the hardcore algebra stage. The next stage, we actually want to optimize. We actually want to optimize this. We actually want to optimize, or actually maybe a better way to talk about it, we want to minimize. We want to minimize this line, this expression right over here. We want to find the m and the b values that minimize it. And to help visualize it, we're going to start breaking into a little bit of three-dimensional calculus here, but hopefully it won't be too daunting. If you've done any partial derivatives, it won't be difficult. This is a surface. If you view that you have the x and y data points, everything here is a constant except for the m's and the b's. We're assuming that we have the x's and y's, so we can figure out the mean of the squared values of y, the mean of the xy product, the mean of the y's, the mean of the x squares. We assume that those are all actual numbers. So this expression right here is going to be, it's actually going to be a surface in 3 dimensions. So you can imagine this right here, that is the m axis. This right here is the b axis. That is the b axis. Let me continue the m axis, and let me continue the b axis. And then you can imagine the vertical axis, the vertical axis here to be the squared error. This is the squared error of the line axis. So for any combination of m and b's, if you're in the mb plane, you pick some combination of m and b, you put it into this expression for the squared error of the line, it'll give you a point. And if you do it for all of the combinations of m's and b's, you're going to get a surface. You're going to get a surface. And it's going to be the surface is going to look something like this. I'm going to try my best to draw it. It's going to look something like this. You could almost imagine it as somewhat of a kind of a bowl, or you can even think of it as a three-dimensional parabola, if you want to think of it that way. Instead of a parabola that just goes like this, if you were to kind of rotate it around and distort it a little bit, you would get this thing that looks kind of like a cup or a thimble or whatever. And so what we want to do is we want to find the m and b values that minimize. Notice this is a three-dimensional surface, so I don't know if I'm doing justice to it. So you can imagine, let me see if I can, you could imagine a three-dimensional surface that looks something like this. This is the back part that you're not seeing. So that's the inside of our three-dimensional surface. We want to find the m and b values that minimize the value on the surface. So there's some m and b value right over here that minimizes it. And to do that, and I'll actually do the calculation in the next video, but to do that, we're going to find the partial derivative of this with respect to m, and we're going to find the partial derivative of this with respect to b, and set both of them equal to 0. Because at this minimum point in I guess you could say in 3 dimensions, this minimum point on the surface is going to occur. This minimum point on the surface is when the slope with respect to m and the slope with respect to b is 0. So at that point, the partial derivative of our squared error with respect to m is going to be equal to 0, and the partial derivative of our squared error with respect to b is going to be equal to 0. So all we're going to do in the next video is take the partial derivative of this expression with respect to m, set that equal to 0, and the partial derivative of this with respect to b, set that equal to 0, and then we're ready to solve for the m and the b, or the particular m and b.